and we're happy to have with us Dr. Jun Wang, who's Process Technology Managers at Ideal. And this is our only fully focused presentation on perovskite solar cells. And she will talk about the application of spatial atomic layer growth for perovskite solar cells. Jun, the floor is yours.
Thank you. Hello, everyone. I'm Jun Wang from Ideal Deposition, and it's very honored here to share this topic about the SALD for the perovskite solar cells. Here is the outline. I'm going to talk about three parts. The first part is about is a brief introduction of Ideal. The second part is about the ALD, and the last part is about the SALD. Ideal was founded in 2013 in Shanghai, and it mainly produced vapor equipment for solar cells, such as LD vision equipment, high capacity tube diffusion, annealing, and oxidation equipment. And the production capacity has reached 400 ALD units per year. ALD allows growing atomically precise, dense, pinhole-free, and conformal films through the sequential exposure of the substrate to the precursor. In this layer-by-layer growth, a precursor gas initially reached with the substrate, and then pushed by an inert gas. A second precursor then reacts with the first precursor absorbed on the substrate, after which it is pushed, completing the deposition cycle. This substrate reaction are self-limiting, yielding one monolayer per cycle, and the purging step prevents the mixing of the precursors, which would otherwise decrease the uniformity of the deposition. The deposition cycle is repeated until the required number of deposition layers is achieved. ALD is widely acknowledged as a powerful technique for the deposition of high-quality layers. The capacity of ALD to generate dense, conformal, pinhole-free layers becomes attractive also for the PSCs. Researchers have mainly focused on the fabricating efficiency electron and hole transport layers, such as tin oxide layer, zinc oxide, nickel oxide, and ultra-thin aluminum passivation layers. However, the need for long purge steps severely limits the throughput of the ALD system. SALD is a variant of ALD, features spatial rather than temporal separation of precursors, where purge steps are not needed, thus increase the deposition rate by orders of magnitude compared to ALD. In SALD, the precursor and the inert gas are continuously flowed toward the substrate through a shell height with multiple channels. The substrate is moved laterally relative to the shell height, being sequentially exposed to the precursors during the movement. The inert gas introduced between the precursors serves as a curtain that prevents the precursor intermixing and steers precursors molecules towards the exhaust. The extent of precursor intermixing is of crucial importance when using SALD, as it affects the uniformity and the property of the deposited films. When precursors are well separated and thus react only with the substrate or previously deposited layers in a layer-by-layer manner, the deposition occurs in the ALD regime, characterized by an overall uniform, dense, pinhole-less, and conformal film growth. In contrast, when there is a significant mixing of precursors, that can react with each other. The deposition occurs in CVD region, resulting in a faster but generally non-uniform and poor quality film growth. Ideal has independently developed 3 types of equipment for PSCs. As we can see here, research and develop line, pilot line, the mass production line. Substrate can be glass, silicon wafer, flexible substrate, and so on. Films such as tin oxide, aluminum, zinc oxide, nickel oxide can be grown at a temperature between 80 and from 80 to 300 degrees C. The maximum size of the substrate that can be placed in the research and development machine is about 300 millimeter by 400 millimeter with 2 pieces. And the coating non-uniformity is less than 3%. It only takes 18 minutes for one round to finish 20 nanometer deposition. The maximum coating size for the pilot line and the production line is about, can be reached about 1.2 meter by 2.4 meter. And the coating non-uniformity can be less than 5%. The mass production line can be configured according to the requirement of the production complexity and the film thickness. The research and the scale machine circular single chamber with a shower height on top, and then a tray and a heater. Shower head is divided into 4 parts with multiple channels of each, flowing precursors inert gas continuously. The substrate is placed on a tray, which is rotary and will be exposed to the precursors as it rotates. The maximum size of the substrate can be about 300 by 400 millimeter. The shape of the substrate is square, round, according to the specific needs. The pilot line consists of loading or unloading platform, a preheating chamber, and a process chamber. Substrate loaded will be loaded on tray, which moves from one side of the line and go through into the preheating chamber to preheat, and then goes into the process chamber for deposition. After the deposition, substrate moves backward out of the line. The mass production line comprises loading platform, a load lock chamber, preheating chamber, process chambers, and a load lock out chamber. The equipment can be modularly equipped with a number of process chambers according to the customer's capacity needs. The substrate placed on a tray moves from the loading side, go through all the chambers, and move out of the line from the load lock out. The substrate is unloaded at the unloading platform, and the tray moves back to the loading platform through the bottom of the chamber. Load lock in and load lock out chambers are for transmission between the atmosphere and vacuum. The preheating chamber and the process chamber are always in a vacuum state. The preheating chambers use infrared lamps as the heating source. Good heating uniformity and heating stability can be achieved by adjusting the powerful distribution of these lamps. The process chamber has a heater to ensure the consistent temperature during the process. In the following, tin oxide and aluminum layer group by ALD will be shared. Different thick film grown on silicon substrate will appear different color. On the top left is the 15 nanometer and 18 nanometer thick tin oxide layer. The film thickness increases nearly with the cycle numbers and the growth per cycle, GPC, is 0.1 nanometer per cycle. Also, the transmittance of tin oxide layer can reach 96% with thickness of 20 nanometer. Tetravalent tin is about 86%, while divalent tin is about 14%. Moreover, the composition of the film could be adjusted by using different amount of precursors. Tin oxide layer SALD could cover the bottom layer very well observed from the SEM. Furthermore, SALD tin oxide could prevent the formation of water effectively. Pre-cycle deposited by SALD tin oxide layer was dipped into water completely. After 3 minutes, the pre-cyclate with 30 nanometer SALD tin oxide layer on top was flooded water. After 5 minutes, the pre-cyclate with 40 nanometer SALD tin oxide layer on top was flooded water. Coating non-uniformity of 300 millimeter by 300 millimeter air is 2.3, merely 9% of the film, and the reflective intensity of the tin oxide layer is about 1.9. Here we see the overall coating area is about 1.1 millimeter by 1 meter on silicon substrate. The coating thickness non-uniformity is about 4.1%, and the average refractive intensity is 1.9 as well. This one, the coating area is about 2 meter by 1 meter on glass. Film thickness at 200 positions were measured, and we can see the lateral non-uniformity and the perpendicular non-uniformity is around 4% and 3% respectively. The overall thickness non-uniformity is about 4%. Next is about the alumina film grown by SALD. The film thickness has a linear relationship with the deposition cycle number as well. The GPC is about 0.1 nanometer per cycle. Transmission of the SALD aluminum oxide layer is about 96%, even though the thickness is as high as 100 nanometer. The coating non-uniformity of 300 by 300 millimeter area is about 2%, and the reflective intensity is about 1.62, which was grown at 100 degrees. A drop of water was used on the perovskite covered by alumina to study the water resistance of the SALD alumina. The result shows that the perovskite was corroded 10 minutes later, which proves the SALD alumina has a good quality to prevent water formation. To sum up, Ideal's SALD equipment process time is short, and the substrate dimension is flexible. It is suitable for large area deposition and mass production. Thank you for your attention.
Thanks, Jun. Very interesting. So maybe a brief question from my side. So also on the market side of things. So we've seen GCL, for example, being now really commercially active in that field, but a lot of companies have been talking. So that means they must have at least some R&D equipment, some pilot equipment. So how are you seeing at the moment the market for equipment? Also, since there are, of course, so many different routes for perovskites.
Well, for the marketing for the PCS, it has different technique for these solar cells. Like for the electron, for example, for the electron layers, it could be grown by vapor deposition, and also the ALD, and also the PCS has different structures, which could be done on the RPD. So, well, it's quite hard to say which will be the winner, but as we know, a lot of companies from the solar cells are more interested in the SALD growth because it's has high deposition rate, and it can grow the film faster, and also it can grow large area, and it's suitable for the mass production. It has quicker take time. So we have confidence that SALD will use widely in this PSC industry.
Okay, wonderful. Thanks so much. You might want to stay a little bit if there's any questions in the chat. So everyone around still, please feel free to ask Jun about any details. Thanks a lot and have a nice evening.
Thank you, Mike.